Parametric equations of a line. Welcome, everyone. Let's begin our lesson on the parametric equations of a line. Now, before we dive into today's new topic, let's quickly recall what we covered in our previous subsection. We learned how to represent a line using a vector equation. Specifically, if we have a line that passes through a fixed point with position vector, and this line is parallel to a direction vector, b, we can write its equation as r equals a plus lambda times b. Now, while this vector form is incredibly concise and elegant, it isn't always the most convenient way to work with specific coordinates in a problem. Often, when we are solving complex three-dimensional geometry problems, it is much more practical to express the individual x, y, and z coordinates of any point on that line separately. This method of breaking the line down into individual coordinate components is what we call the parametric equations of a line. In the next few slides, I will show you exactly how we derive these equations from the vector form we just discussed. Understanding the concept. Now that we have established the vector equation of a line from our previous slide, let's take a moment to really understand the concept behind the term parametric. When we call these parametric equations, we are text referring to the use of a parameter, which, in this specific case, is the scalar lambda $. You can think of this lambda as the engine of our equation. Essentially, the parameter lambda acts as a scaling factor. It takes our direction vector and stretches, shrinks, or reverses it. As lambda varies over all real numbers, meaning it can be any value from -infinity to +infinity, the point P, with coordinates x, y, and z, moves along the entire length of the line in three-dimensional space. This movement is what allows us to describe every single point on the line, not just one. In the next slide, we are going to see exactly how we can break this down into individual components through a step-by-step derivation. Step-by-step derivation. Now that we understand how the parameter lambda acts as a scaling factor to move us along the line, let's look at how we actually arrive at these parametric equations. We are going to derive them by expanding the vector equation we saw in the previous slide, which is r equals a plus lambda b. To start our derivation, in step 1, we need to define our vectors in component form. Instead of looking at them as single arrows, we are going to break them down using our standard unit vectors, I hat, j hat, and k hat. First, let's represent the position vector of any arbitrary point P with coordinates x, y, and z on our line. We write this as r equals x I hat plus y j hat plus z k hat. Next, we do the same for our fixed starting point, point A, which has the coordinates x sub 1, y sub 1, and z sub 1. So, the position vector A equals x sub 1 I hat plus y sub 1 j hat plus z sub 1 k hat. Finally, we define our direction vector, b, which is parallel to the line. We represent its components as a b and c, giving us b equals a I hat plus b j hat plus c k hat. By breaking the vectors down this way, we'll be able to perform the substitution and grouping that we'll see in the next slide. Step-by-step derivation continued. Now that we have defined our vectors in their component forms, representing our arbitrary point, our fixed starting point, and our direction vector, let's move on to step 2, where we actually perform the substitution. We are going to take those component forms we just identified and plug them directly into our original vector equation, which is r equals a plus lambda b. When we do this, we see the left side of the equation expressed in terms of x, y, and z with their respective I, j, and k unit vectors. And on the right side, we have our starting point coordinates plus the scalar lambda multiplied by our direction components. Moving on to step 3, our goal is to group the components together. To do this, we first distribute the scalar lambda across the direction vector. Once that's done, we group all the terms that share the same unit vector. Notice how the right side of the equation now clearly shows the I components, the j components, and the k components bundled together. This leads us to the most crucial part, step 4, equating the coefficients. Now, remember a fundamental rule of vectors. Two vectors can only be equal if their corresponding components are identical. Therefore, for the left side to equal the right side, the coefficient of the I vector on the left must match the I component on the right, and the same must hold true for the j and k components. By doing this, we arrive at three separate, simple equations. X equals x1 plus lambda times a, y equals y1 plus lambda times b, and z equals z1 plus lambda times c. These three individual equations, which we have just derived from the single vector equation, are what we call the parametric equations of the line. This derivation is important because, as we will see in the next slide, it allows us to treat the movement along a line, like a drone in flight, as a function of a single variable, lambda. Real-world analogy: the flight of a drone. Now, I know that all those algebraic derivations we just went through in the previous slides might seem a bit abstract. So, to help you visualize what is actually happening, let's step away from the math for a moment and use a real-world analogy: the flight of a drone. Imagine you have a drone sitting on a launch pad at a specific coordinate in the sky, which we will call point A, with coordinates x sub 1, y sub 1, z sub 1. Now, this drone is programmed with a specific flight path. It is set to fly in a constant, straight direction, and this direction is defined by our direction vector, b, which is composed of the components of b and c along the I, j, and k unit vectors. Here is the most important part to help you understand the math. In this scenario, you can think of our parameter lambda as time. Think about it this way. At time lambda equals 0, the drone hasn't moved yet. It is still right at its starting point, point A. As time passes, as lambda increases, the drone moves further and further along that programmed direction, vector b. By using the parametric equations we derived in the last slide, we can actually calculate the exact position of the drone, its precise x, y, and z coordinates, at any specific moment in time, lambda. This brings us to the next slide, where we will apply this exact logic to solve a concrete numerical problem. Worked example. Here is our problem. We need to find the parametric equations of a line that passes through the point 2, -3, 5, and is parallel to the vector b, which is 4i plus j minus 2k. To solve this, let's follow a clear three-step process. Step 1, we must identify our given values from the problem statement. Looking at our point, we can see that x sub 1 is 2, y sub 1 is -3, and z sub 1 is 5. Next, we look at our direction vector to find our direction ratios. Here, A is 4, B is 1, and C is -2. Step 2, now, we apply the general parametric formulas we derived earlier in the lesson. We will use the templates where x equals x sub 1 plus lambda times a, y equals y sub 1 plus lambda times b, and z equals z sub 1 plus lambda times c. Step 3, this is where we substitute our specific values into those templates. For the x-coordinate, we plug in 2 and 4, which gives us x equals 2 plus 4 lambda. For the y-coordinate, we substitute -3 and 1, resulting in y equals -3 plus lambda. And finally, for the z-coordinate, we use 5 and -2, which simplifies to z equals 5 minus 2 lambda. So, our final answer is: the parametric equations of the line are x equals 2 plus 4 lambda, y equals -3 plus lambda, and z equals 5 minus 2 lambda. Now that we have derived the formulas and understood the concept using our drone analogy, let's put everything into practice with a worked example. As we move to the next slide, I want you to pay close attention because I will highlight some common pitfalls where students often make mistakes during this exact substitution process. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the derivation we just went through, it is very easy to make small mistakes that can lead to the wrong final answer. First, watch out for confusing your points with your directions. This is perhaps the most frequent error I see. It is easy to accidentally swap the coordinates of your starting point, which we called x sub 1, y sub 1, z sub a, with your direction ratios, a, b, and c. To keep this straight in your head, just remember, the point is your fixed anchor. it is where the line starts or passes through, whereas the direction ratios act like a compass, defining the direction in which the line is going. Second, be extremely careful with sign errors. When you are substituting values into your formulas, especially if the point or the direction vector contains negative numbers, you must maintain those signs strictly. For instance, if your y-coordinate, y sub 1, is -3, and your direction component, b, is -2, your equation must be y equals -3 minus 2 lambda. A common mistake is to accidentally change that subtraction to addition, which completely alters the path of your line. Finally, do not forget to include the parameter itself. Sometimes, in the rush to simplify, students leave out the lambda. Remember, without that parameter, you no longer have a moving point or a line, you are left with just a single, static point in space. We need that lambda to allow the point to move along the line. Keep these three things in mind, and you will find much more success with these problems. Now, let's quickly review the key takeaways from today's session. Key takeaways. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. First, let's revisit the definition. Remember, parametric equations are a way to describe a line by expressing each of its coordinates, x, y, and z, as individual functions of a single scalar parameter, which we call lambda. Instead of looking at the line as one single vector, we are looking at how each coordinate changes independently as lambda varies. Next, let's look at the formula one more time to ensure it's etched in your memory. If you are given a line that passes through a specific point with coordinates x sub 1, y sub 1, and z sub 1, and you have the direction ratios a, b, and c, you can write your equations as follows. X equals x sub 1 plus lambda times a, y equals y sub 1 plus lambda times b, and z equals z sub 1 plus lambda times c. Just remember to plug in your starting point and your direction components exactly as we practiced in our worked example. Finally, it is crucial to understand the relationship between what we've learned today and our previous lesson. These parametric equations are not a brand new concept. They are simply the scalar components of the vector equation r equals a plus lambda b when we break that vector equation down into its I, j, and k components. As we did in our step-by-step derivation, we arrive exactly at these parametric forms. If you have mastered these 3 points, you have a solid foundation for working with lines in three-dimensional space. Great job today!